Good morning, students. In the today, the operating system lecture series, we will discuss a very important topic that is called deadlock. In a multi-programming environment, several processes may, you know, compete for the finite number of resources. A process requests resources if the resources are not available at that time. The process enters a wait state. Waiting processes may never again get change state because the resources they have requested are held by other waiting processes. So now you got this thing that let's just wait. Waiting for the slides to change. So this is the deadlock. In this we will discuss the deadlock characterization, resource allocation graph. So what I am saying, a process in operating system uses different resources and use resources in following ways. A process, requesting a resource, use the resource and release the resource. So if a particular process requests a resource which is occupied by another process, so it is not get that resource. As I have told in this, a process requests a resource, the resources are not available at that time, so the process enters a wait state. Waiting process may never again change state because the resources they are requested are held by other waiting processes. So a very good example is that okay. So now just share again the screen. I think there is some problem. Okay. So deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. I mean to say, if suppose there are two processes and there are two resources, so a process is hold a resource and waiting for another resource. So waiting for another resource which is actually acquired by another process. Let's see this example. When two trains are coming towards each other on same track and there is only one track, so none of the train can move once they are in front of each other. Similar situation occur in operating system when there are two or more processes which are hold the resource and waiting for the resource held by other. So that is called a deadlock. I think you now understood the deadlock. Let's see this deadlock with the help of a figure. Let's see there are two processes. One is the process P1 and another is the process P2. So the process, and there are two resources, resource 1 and the resource 2. Resource 1 is assigned to process 1 and the resource 2 is assigned to the process 2. Process 2 is waiting for resource 1 and the process 1 is waiting for resource 2. Since resource 1 is acquired by process 1 and this resource 2 is assigned to process 2, since these two processes holding a resource and waiting for a resource which is occupied by others, so this is called a deadlock state. In this diagram, the process 1 is holding resource 1 and waiting for resource 2, which is acquired by process 2, and process 2 is waiting for resource 1. So this is a condition of the deadlock. They will never, get the resources since the resources which are seeking that is held by another process. Now, deadlock characterization. So in a deadlock, processes never finish executing and system resources are tied up, preventing other jobs from starting. Okay, so a deadlock situation can arise if the following four conditions hold simultaneously in a system. The first one is called the mutual exclusion. So at least one resource must be held in a non-shareable mode. That is, only one process at a time can use the resource. If another process requests that resources, the requesting process must be delayed until the resources has been released. The second, the condition is called hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. So a process must be simultaneously holding at least one resource and waiting for at least one resource that is currently being held by some other process. Third one is called the no preemption. The resources cannot be preempted, that is, a resource can be released only voluntarily by the other holding, by the process holding it after that process has completed its task. The fourth one is called the circular wait. Let's take a set P0, P1, Pn of waiting processes must exist such that P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that is held by P2, and so on, and Pn minus 1 is waiting for a resource that is held by Pn, and Pn is waiting for a resource that is held by P0. So that is called, this is called a circular wait. P0 is waiting for P1, P1 is waiting for P2, P2 is waiting for P3, Pn minus 1 is waiting for Pn, and Pn is waiting for P0. So it will form a circular waiting. So that is why it is called a circular wait. So these are the four conditions that are necessary to achieve deadlock. It means a deadlock to achieve there are four conditions which are existing. One is called mutual exclusion, hold and wait, no preemption, and circular wait. Now, resource allocation graph. In some cases, deadlocks can be understood more clearly through the use of the resource allocation graph, having the following properties. A set of resource categories R1, R2, R3, Rn, which appears as square nodes on the graph, dots inside the resources nodes indicate specific instances of the resources, that is, two dots might represent two lesser printers. A set of processes P1, P2, P3, Pn request each a set of directed arcs from Pi to Rj, indicating that process Pi has requested resource Rj and is currently waiting for that resource to become available. Assignment is a set of directed arcs from Rj to Pi, indicating that resource Rj has been allocated to process Pi and that Pi is currently holding resource Rj. Note that a request age can be converted into an assignment age by reversing the direction of the arc when the request is granted. However, note there is where is the additional whereas assignment age estimates that particular instance do not have this box. So now this is a resource allocation graph. The process P1, is holding a resource, holding an instance of the resource R2, okay, and waiting for a resource of R1, and the process P2 is also holding an instance of the resource R2 and waiting for a resource of R3, and process P3 is holding an instance of the resource R3, and there is a resource R4 which is having some instances of resources. So this resource allocation graph, one instance of the resource type R1, two instances of resource type R2, one instance of resource type R3, and the three instances of the resource type R4. Process state. Process, as I told you, P1 is holding an instance of resource type R2 and is waiting for an instance of resource type R1. As I have told this scenario earlier. So given the definition of a resource allocation graph, it can be shown that if the graph contains no cycle, then no process in the system is deadlock. If the graph does contain a cycle, then a deadlock may exist. If each resource type had exactly one instance, then a cycle implies that a deadlock has occurred. If the cycle involves only a set of resource types, each of which has only a single instance, then a deadlock has occurred. Each process involved in the cycle is deadlock. In this case, a cycle in the graph is both a necessary and a sufficient condition for the existence of deadlock. If each resource type has several instances, then a cycle does not necessarily imply that a deadlock has occurred. In this case, a cycle in the graph is a necessary but not a sufficient condition for the existence of deadlock. To understand this concept, let us return to the resource allocation graph as shown in this figure. Suppose that process P3 request an instance of resource type R2. Since no resource instance is currently available, request age P3 tending to R2 is added to the graph. At this point, two minimal cycles exist in the system: P1, R1, P2, R3, P3, R2, and P1, and another will be the P2, R3, P3, R2, and P2. Okay, so two cycle would be existing in that case. So if that will be the case, you are saying the two, this cycle exists, then this is the resource allocation graph with the deadlock. So the process P1, P2, and P3 are deadlocked. Process P2 is waiting for the resource R3, which is held by a process P3. Process P3 on the other hand is waiting for other process P1. A process P2 to release resource R2. In addition, process P1 is waiting for process P2 to release resource R1. Now consider the resource allocation graph, um, uh, which uh, which is having this resource allocation, which is having a cycle but no deadlock. Let's see that also. P1, P1, R1, P3, R2, and P1. However, there is no deadlock. Observe that process P1 may release its instance of resource type R2. That resource can then be allocated to P3, breaking the cycle. So if a resource allocation graph does not have a cycle, then the system is not in a deadlock state. On the other hand, if there is a cycle, then the system may or may not be in a deadlock state. This observation is important when we deal with the deadlock problem. Okay, so these things will be taken care, or took into the considerations. Now these are the references, and So this thank you students, thank you for patience hearing, and here I'm stopping. In the next we will discuss method for handling deadlocks, and this is the next topic would be the the methods for handling deadlock. Thank you. uh, okay, so this is stops here now. Stop.